Let's go ahead and get started. So today, I'm just going to go through section 4. Should be pretty short. There's not too much to go over. So I'll go through the conformational isomers, chirality, enantiomers, absolute configuration, diastereomers, and then meso compounds. So we started with conformational isomers. So these are isomers that are formed by rotation around a CC single bond. Because this has free rotation, it can just move however it pleases. So we have the same connectivity, but just different structures. And the two that we pay attention to are eclipsed and staggered conformation. And the staggered conformation is going to be more stable because you have all your groups spread out to the best of your ability. So these are Newman projections. That's just how we show conformations around a CC bond. So staggered, this is propanol. So this carbon here, or this dot here, is this carbon. Let me get my pointer. So this dot here is this carbon, okay? And we have two hydrogens on there and an OH group here. And then back here, the center of this circle is this carbon here. And then that carbon has two hydrogens and a methyl group on it. So you're just looking at it from head on here. So I didn't build this specific molecule, but this is ethane. So staggered is when you're looking at it from this direction, and then the back atoms are lined up in the middle of the front ones. So as you see, this gives like the most amount of space between all these groups. So all these electron clouds are as far apart as possible. They're happy, they're not touching. They're not going to push on each other and cause any strain. So this staggered conformation has the lowest energy. And then eclipsed is when they're all lining up when you look at it from head on. And then these electron clouds, these groups, are going to be closer together than we would like. So they're going to be pushing on each other, which is going to cause strain, and it's going to be higher in energy, so less stable. Makes sense? And then there's the example with, what was it? Or the butane, right, that we went through, where it has, like, depending on the angle, you have staggered eclipse, but then there's a staggered that's more stable. So if you have bigger groups like this, this would be the most stable if one of these bigger groups were on the other side, right? Because that would be the most amount of space between those big groups. So it does change depending on what angle you turn. But in general, staggered is going to be more stable than eclipsed. And this is how we draw eclipsed. We just draw the lines a little bit past the first line, just so we can see it, but that means that they're lined up.
They're like directly behind each other.
Mm-hmm. Okay. Yeah, we just draw it like that so we can see the lines there, but that means that it's exactly lined up. Make sense? All good? Okay. Stop it. So chirality, a molecule is chiral if it has, or a carbon is chiral if it has 4 different groups attached to it. So being chiral essentially means that the mirror image of that molecule is non-superimposable. So, for example, actually I'm going to wait and show you that later. Never mind. Okay, so to be chiral, it has to be an sp3 hybridized carbon, because we need to have 4 different groups, and sp3 carbons have 4 bonds, right? So we have like an sp2 carbon like this one here. There's no way that could be chiral because we have a double bond. So we're not going to have 4 different groups attached to it. Okay. And those groups with the 4 different, or the atoms with the 4 different groups are called chiral centers. So achiral just means the opposite of that. It means that it does not have 4 different groups attached to it. And that means that the mirror image of that molecule would be superimposable. So I explained this earlier, but do you guys know what superimposable means, the people that came in? Yeah. Yeah, so you can put it on top of each other and it looks the same and you can't tell the difference. Okay, so a few examples. So you had to do this on the homework. Just pick out the chiral center. So on this molecule, so I can check, this carbon has 3 hydrogens on it. That's not a chiral center. This one has 3 hydrogens on it, not a chiral center. This one maybe looks like a chiral center, but we have a hydrogen chloro group and then 2 methyl groups. So because I have 2 methyl groups, those are identical, so that's not a chiral molecule. Okay. And then this one here, so this first carbon that has 3 hydrogens on it, that's not chiral. The second one, I have an OH group, I have a hydrogen, I have an ethyl group, and a methyl group. So that's 4 different groups. So this one right here is chiral. And then the other ones have multiple hydrogens on them, so not chiral. So in terms of rings, this carbon here has a methyl group on it. It has a hydrogen also attached to it, not shown. And then it's connected to this whole half of the ring and this whole half of the ring. So because this ring is symmetrical and both of those halves are identical, this is not going to be chiral because those halves of the ring are the same. Does that make sense?
I have a question about, so the top one, it doesn't have a chiral center, but is it achiral? It is.
Yeah. So not, if it doesn't have a chiral center, it is achiral.
Okay. Yeah. So there's not like an existence between the two.
No.
Like you're there. Okay.
No.
That's what I was
Okay. So, but in terms of this one, so this carbon here has a methyl group. I have a hydrogen, and then it's connected to this whole half of the ring, and then this whole half of the ring. But now, since I have that double bond there, these halves of the ring are not identical anymore. They're not symmetrical. So those halves of the ring are different. So I have 4 different groups. So this carbon here would be chiral. Make sense? Okay, and I think there was some on the homework, let me know if I'm mistaken, that like kind of look like this. Did you see that on the homework?
Yeah.
Yeah, so if you didn't know what that means that this half of the ring is in front of the plane, because we normally show the rings like this, where the whole ring is in the plane, and then you'll have the groups on the ring, either in or out of the plane. But if it's drawn like that, that means just like the front of the ring is, here's my plane, the front of the ring would be in front of the plane, just if you come across that. He won't have that on a test or anything, but if it comes up in homework again. Okay, so enantiomers are mirror images of each other. So if a molecule is chiral, its mirror image is non-superimposable. So its mirror image is not the same molecule. And these are enantiomers. So I did build these. So I have carbon here. I have hydrogen, chlorine in the plane, and then I have OH in the front, and pretend this is a methyl group. I didn't want to get too messy here. Okay, and then it's mirror image. So I have the hydrogen here, chlorine here, oxygen here, methyl in the back. So these are mirror image, right? We can see that. But if I try to like turn this around so I can put it on top of each other, these 2 groups aren't going to line up, right? So that's what it means by non-superimposable, is if I try to turn this around to put it on top of each other, they don't look alike because they're different molecules. So these are enantiomers. And when you have enantiomers, one will be in S configuration and one will be in R if there's one chiral center. And then the special characteristics of enantiomers is that they have different optical activity, so they'll rotate polarized light in different directions. I don't really know what that means, but just in terms of like, I don't know, actual like real life lab, I don't know what that means, but like how do you measure the rotation of light? I don't know, but I don't think that's it, but maybe. I feel like it's more complicated than that. Okay, so absolute configuration, that's a way to identify between enantiomers. So we assign absolute configuration by assigning priorities to all the groups on the chiral center, and priorities are assigned based on atomic number. And then if the first atom is the same, you go on to the second group of atoms. And then to figure out absolute configuration, your least priority group has to be in the back of the plane because you're only paying attention to how groups 1, 2, 3 are arranged. So 4 always has to be in the back before you can determine that. So if groups 1 through 3, 1, 2, 3 are arranged in clockwise direction, then it's going to be an R configuration. If it's in counterclockwise, it'll be S. So we have some examples. Okay, so this is my chiral center, right? So I have an ethyl group on that side. I have a methyl group. I have OH here, and then I have, hello. And then I have hydrogen in the back. Okay, so I know hydrogen is my 4th priority group. So I know oxygen will be my first, or the OH group will be my first, because oxygen has higher atomic number than carbon. And then ethyl will be 2, methyl will be 3. Okay, so because 4 is already in the back, I don't have to switch any groups around. So 1, 2, 3 are going counterclockwise. So that's going to be S, or that's not counterclockwise. Is that clockwise?
Yeah.
Yeah, that's clockwise. So that will be an R configuration. Okay. So this one, this is my chiral carbon there. Stop doing that. So this time, if I have an OH in the back, my hydrogen is in the front now. Okay. So, and then I have the right side of the ring and the left side of the ring. So my OH group is going to be number 1, right? So oxygen is higher than carbon. Hydrogen will be 4. And then the side with the double bond is going to be a higher priority than the other side. Does that make sense? Right? Because we went over today how the double bond basically means you're attached to whatever atom that is twice. Okay. So, can you see this color? Should I change color? Okay. Should I change it, or can you see it? Was that yes to it? Okay. Okay. I might change it. I'll change black. Okay, so now my least priority group is in the front. I don't want it in the front, I want it in the back. So my first priority group is in the back right now. So I'm going to switch 1 and 4. And remember to keep your lines all the same. So I'm not moving my lines, I'm just moving the groups. So I switch the first priority group and the 4th priority group to get the 4th one in the back. Okay, so now that 4 is in the back, now I can tell which way it is. So from 1, 2, 3 is going counterclockwise. Okay, so this molecule here is an S configuration, but because I switched 2 groups, I flipped the configuration from the original. So I have to flip it back. So the original will be an R. Okay, does that make sense, right? So from here to here, yes.
do I have to switch them?
Because when you're trying to figure out absolute configuration, you're just paying attention to the way that groups 1 through 3 are arranged. Okay? So if I want to tell how these are arranged, rather like this way or this way, I want this in the back so I could ignore it, right? Because if this is like here, then like it doesn't make sense anymore. Does that make sense?
So I need to make sure that my highest OH is in the front.
No, you need to make sure your hydrogen is in the back. So you're going to switch with, yes, the lowest is in the back. Okay, yes, because you're just paying attention to 1, 2, 3. So you're going to switch the two groups. You'll switch the lowest priority group and then whatever group is already in the back. Does that make sense? So it won't always be 1 and 4. Sometimes it'll be 2 and 4, 3 and 4. It just depends on what's already in the back. Does that make sense? Okay. Because he was like, when he was going over in class, yeah, Victoria.
It made a lot more sense once he explained it today.
Yeah.
And that was very lost.
Yeah, when he was explaining in class, he explained it like a steering wheel. Like this is. Does that not help? Okay, I mean, I don't know how well this helps you, but like the least priority group is in the back, and then this is my steering wheel, and I'm trying to figure out which way it's going. I don't know if that helps at all, but.
In class, people like do random stuff and go, it's S, so because it's S, we call it R. And I'm like,
Okay, so from here to here, I switched two groups, right? So from this molecule to this molecule, when I switched two groups, I made this molecule's enantiomer, right? Yes, so if I made enantiomers, one has to be an R, one has to be an S. So if I switch two groups, I made the enantiomer, which is going to be the opposite configuration of the original. Yes?
So like, but which one is the answer? The one in red or the one in white? Like, which, like on a test, he gives us that, what's the correct answer?
The
R?
correct answer would be R,
yeah.
Okay.
okay? Because I had to switch the two groups to figure out what this one was. Okay. Because the least priority group is not in the back. So you cannot tell because, okay. So if I try to do this here, I have 1, 2, 3, and then I'm going this way, right? So if I try to do 1, 2, 3 this way, then it would tell me that it's S, right? And it's not S, it's R. So it doesn't work unless your least priority group is in the back. Good. Okay. So yeah, so I have to switch the two groups so I can tell what the configuration of this one is. You're good.
He never said that, like during our class. Like, he never said that the least priority group had to be in the back.
That's awkward.
That was
That's kind of important. Yeah, so the least priority group has to be the back.
The crooks.
Okay, so then when I put it in the back,
I was like, why is he flipping the groups? Like, and I was trying to think, I was like, what is he doing?
okay,
Makes a lot
are we
of
all right?
sense. Yes.
Yeah. So we switched the two groups, then the least priority group is in the back. Now I can tell what this one is, okay? But when I tell what this one is, it's actually the opposite of the original because I switched the two groups.
And if the least priority group is already in the back, then you don't have to flip it.
Mm-hmm. Yes. Or the alternative is you can switch 1 and 4 and 2 and 3, and that will give you the original. I don't like doing that personally. I just like flipping it back, but you can do that if you so please.
So if you're looking at this one,
Mm-hmm.
right, the white one,
Mm-hmm.
and you flip it, like during a text, if you just flip it in your mind, you have to write down the enantiomer.
Yeah, you'll have to show you switching the groups. Because, I mean, if you just put down the answer, then you got a 50-50 shot, so that doesn't really show that you have any knowledge on the subject. So you have to show the switching to get credit.
How many of these problems do you think will be on the test?
We just have the final left, right? We don't have another
Yeah.
test?
Actually, yeah.
Yeah, so not probably one. It's going to be more heavily on section 5, so the SN1, SN2 reactions. You will have to know this stuff for those reactions because of the configuration flips and everything in those reactions. But in terms of actually just assigning absolute configuration, not very many. I think maybe one I wouldn't count on too much of it. Yeah, all good? Okay, last one. So, this is my chiral carbon, right? Okay, so chlorine, if you look, that's 17, right? So, chlorine will be my first priority group. OH will be number 2. And then between the methyl group and the carboxyl group, I can obviously tell that this carbon is connected to 3 hydrogens, right? This one's connected to 2 oxygens, but 1 oxygen twice, so more or less 3 oxygens. So this one will be higher priority than this. So this will be 3, 4. Okay, so this is my lowest priority group. It's not in the back, it's in the plane, so I need to switch with whatever's in the back. Yes, so 2 is in the back right now, so I'm going to switch 2 and 4. Okay, so 1, 2, 3, 4. So now the 4 is in the back. Now I can figure out where it is. So I have 1, 2, 3 going in this direction. So that is S. So that means this molecule is an S configuration, which means the original was an R configuration. Are we following that? All good? Any questions? Are we good, Haley? Whispers in the corner. Okay. So sorry. Okay, all good to move on? Okay, diastereomers. This really isn't that important. The most important part of this section is the absolute configuration and knowing how to sign that. Diastereomers are 2 molecules that have the same connectivity but different structures, but they're not mirror images. So they'll have 2 or more chiral centers, and we could have like SR or SS. So these 2 are enantiomers because I have SS and RR, which means these are mirror images. But if I have SR and SS or like RR, SR, they won't be mirror images anymore, but they'll still be isomers because they have the same connectivity. So we call those diastereomers. Again, that's not really that important. And then last thing, meso compounds. So meso compounds will have an even number of chiral centers, and you'll have a mirror plane somewhere in the molecule. So here, I have a mirror plane here. This carbon is an S configuration, this one's an R. This should be a wedge here, I don't know what happened there. But these 2 sides are mirror images of each other, so I could fold them like a book.
Methyl group on the left.
Yes, yeah. I don't know what happened here, but yeah, that's supposed to be a wedge and this is supposed to be a methyl group. My bad. Yeah, but these are mirror images. You can fold them like a book. And the important part of this is that either side of the mirror image, either side of the molecule will cancel each other out so they won't have optical activity. Make sense? Alrighty, my friends. If there are no questions, then that's all I got on this section.
I have one. On like the homework today, I don't know if you kind of like did this with your class, but the question that he was like, that's like you're supposed to say if it's identical to A and all that. And like none of them were identical, not even any, they didn't even look the same, but he said they were all identical because he like did something cracked.
Right. Do you have your book with you?
No.
Well, that's quite inconvenient, isn't it? So, let me think if I can draw this out.
They were
Basically, it's just you're just assigning absolute configuration. So the first one I think was in like R or something, and if all excuse me. So if the ones after that will if they're an R, they're identical to the first one. If they're an S, then they're not identical.
And they're mirrored images, is what he said.
Yes.
And so even though they look nothing alike, if they're all R, they're identical.
Mhm.
Because when he asked the question,
I mean, they have to have the same groups, but
they have the same groups,
Mhm.
but like they weren't like oriented the same.
Right,
Like,
right,
at all. And so that like messed me up.
yeah. So you just have to assign absolute configuration, put the lowest in the back, and then do your thing. And if there are, they're identical. If they're S, they're not.
Yeah, is